Alright, morning everybody. I'm Charles Lee. I'm giving my 6-minute talk on the equivalence ratio. So what is the equivalence ratio? So the equivalence ratio is used in combustion studies. So just to remind you that combustion is a rapid chemical reaction involving oxygen in a fuel mixture, producing heat, light, and exhaust properties such as carbon, or exhaust products such as carbon dioxide and water. This equivalence ratio is used to indicate quantitatively whether a fuel oxidizer mixture is rich, lean, or stoichiometric, where stoichiometric refers to the exact amount of oxidizer needed to completely burn a quantity of fuel. Lean refers to if more than a stoichiometric quantity of oxidizer is supplied, and then rich refers to if less than a stoichiometric quantity of oxidizer is supplied. So basically, the equivalence ratio is just trying to determine what is that ratio of your air and fuel coming together in that combustion process. So practical applications, like I said, so it's using combustion, so any processes that involve combustion, so your IC engines, so again, equivalence ratio can help control the power output, the emissions, the fuel efficiency, and knock tendency. So knocking occurs when the air-fuel mixture is in the cylinder, doesn't burn smoothly, so essentially part of the mixture spontaneously explodes early, creating a sharp pressure spike, and these pressure spikes hit the piston and cylinder walls, which gives you the characteristic knocking sound in your car. They're also using gas turbines and jet engines, so again, we can minimize NOx emissions. For gas turbines, NOx emissions are minimized at extremely lean conditions. If it's too lean, it could cause flame instability or blowout. If it's too rich, it could cause overheating or turbine flame damage. And then kind of, as I've said, it's also used in pollution control and environmental monitoring. Depending on how much air and fuel you have going in, you could produce more emissions depending on what you have. So relevant equations, kind of how it's calculated. So typically it's hydrocarbons that are used for your fuel in most combustion processes. So that's something with the CH, such as methane or propane. And mixing it with air, that's going to be your chemical equation up at the top. Again, if you notice kind of right here, this is what air is right here. Air is 21% oxygen and 79% nitrogen by volume. So if you convert it over to moles, we're going to get, for every 1 mole of oxygen in air, there's 3.76 moles of nitrogen. So that's where that comes from. To find the stoichiometric air-fuel ratio from this equation right here, we need to know the number of moles of air, where A is the number of moles of air, which is given by your X and your Y, which are your coefficients on your hydrocarbon. And then knowing that, we can find our equivalence ratio here, which is a emissionless property, which tells you stoichiometric conditions, which again is your ideal conditions, your perfect amount. Then compared to what you're actually burning, then that will give you your stoichiometric, where it equals to 1, you'll be at stoichiometric. If it's less, you'll be burning lean. If it's greater than 1, you'll be burning rich. So with regards to thermodynamics, there's kind of a big one in kind of combustion study, which is adiabatic flame temperature. Again, this is an ideal process. So again, in constant pressure, adiabatic compression, the adiabatic flame temperature is determined from the first law of thermodynamics, which is going to be your H reactants equals your H products. The equivalence ratio will determine how much chemical energy is released, whether combustion is limited by fuel or by oxygen, and how much dilution, this will be your excess air or unburned fuel, affects the final temperature. So again, the result is, at stoichiometric, you're going to have your maximum flame temperature, and if it's greater or lower, if it's greater than or less than 1, you're still going to be lower because of the excess air absorbed in heat if you're burning lean, and if you're burning rich, you're more unreactive fuel absorbed by the heat. In terms of composition of products, this is going to be primarily for emissions coming in, or going out. So using equilibrium thermodynamics, the product species depend on the equivalence ratio. I have an example at the very end where I'll kind of talk more about this. But for rich mixtures, you're going to have more CO and H2 and unburned fuel, and then less CO2 and water, which are your ideal products. And then for lean mixtures, you're going to have extra oxygen and nitrogen in the products. And again, I'll have an example at the end that kind of shows a little bit more on this. And this directly changes flame speed, pressure rise, and for IC engines, their performance. So kind of what are the properties of stoichiometric versus lean versus rich? So for stoichiometric, the pros are that you'll have maximum thermal efficiency for many flames. It's best for combustion completeness, and it produces a strong, stable flame. The cons are, since it's a high flame temperature, you're going to have higher NOx emissions. This could be your nitric oxide and your nitric dioxide. Those are very strong emissions that we really need to try and lower. We can call it, if you're burning a stoichiometric, and cause knocking engines. And then not fuel efficient for continuous systems such as gas turbines and furnaces. And we want to use stoichiometric when balancing power and emissions. So when you're burning lean, the pros are it produces the highest fuel efficiency, the lowest amount of carbon monoxide and HC and soot emissions, the lower flame temperature for lean, or it produces, since it is a lower flame temperature, it will produce lower NOx or emissions. The cons are that the flame speed decreases. Lean mixtures can cause stalling or poor throttle response in IC engines. We typically want to operate lean, so for gas turbines, lean premix combustion minimizes NOx. And then for fuel economy, modes and cars, lean mixtures improve miles per gallon. And then lastly, for rich, the pros are lower NOx emissions due to lower flame temperature, higher power output in the spark ignition engines. The cons are it produces CO, soot, and burn hydrocarbons. Again, those are your emissions. It has poor fuel economy, and it has a lower efficiency because you're going to be wasting chemical energy. And we're going to want to operate rich because it produces a higher powered engine operation. And then rich mixtures also burn faster and cooler, and which prevents knock. So lastly, there's kind of a very basic example. So we'll have propane burning with air, and it's coming in at an air fuel ratio of 18:1. So we want to determine the equivalence ratio. So again, going through our chemical equation, we'll be able to find our number of moles of air, which is going to be 5. We can plug it into our air fuel stoichiometric equation, knowing the molecular weights of air and the fuel, which is going to be propane. And then we can find the air fuel stoichiometric ratio is 15.6, and then plugging it into our equivalence ratio, we can see that it's burning lean, which is going to be less than 1.87. So like I said earlier, since we're burning lean, this is the stoichiometric condition. So in practice, or in reality, if we're burning lean, there's actually going to be an oxygen term right here. This is going to be given by mole representation, be FO2, and we have to calculate those differences because it's going to be, you're going to be burning different compositions because you're not stoichiometric. And with that, these are my sources. Does anybody have any questions?